So today we're going to discuss the last section of this unit called ions. So an ion is a charged atom. So up till now, we've been talking about electrons and protons being the same amount, so making the atom neutral. Now we're going to talk about when the number of electrons changes. So a neutral atom, and then we add or remove electrons. We can never remove protons because, like we talked about before, if we remove protons, that changes the identity of the element. So, for example, sodium has 11 protons because we know sodium's atomic number is 11. If we change the number of protons, it wouldn't be sodium anymore. It would be some other element. But we can change the number of electrons. So, for example, if we remove one electron from sodium, we know originally we had 11 protons, which means if it's neutral, we had 11 electrons. Now, if we remove an electron, the number of protons has not changed. It's still 11. But if we move an electron, now we have 10 electrons. So we have 11 protons, 10 electrons. This gives the sodium atom a +1 charge, okay, because protons are positive, electrons are negative, so we're kind of subtracting them. Well, 11 minus 10 is +1. And we can also write an equation to represent this. So here's sodium, our neutral atom, and then we're losing that electron, so here it is by itself, and then here's our Na +1. There are two specific types of ions. Okay, the first type is a cation. This is where one or more electron is lost from the neutral atom, and because it's lost, just like with the sodium, it gives the ion a positive charge. All metals form cations. Now, you kind of have to think backwards here because we're losing an electron, but we're making the charge positive, and those don't seem to go together. But you have to remember that electrons are negative. They're negatively charged, and so losing one is taking away a negative. So it's kind of opposite thinking. Let's look at another example. Mg2+ is the magnesium ion, and so we took magnesium, took 2 electrons away, and now we have Mg2+. So notice that for all the metals, we're forming cations, and the way that we name it is just the element name and then ion. The other type of ion is the anion. This is where one or more electron is gained by the neutral atom. So because we're gaining negative things, it's giving the ion a negative charge. And so all anions are negatively charged, and all nonmetals form anions. So metals form cations or lose electrons. Nonmetals form anions or gain electrons. So for example, if we take chlorine, Cl-1 is now the chloride ion. So whereas with cations, it's just the element name, with anions, we change the ending to an IDE. So chloride ion, not chlorine ion. So here's our neutral chlorine atom plus an electron, and now we're producing the chloride ion, which is Cl-1. An ion is never formed by changing the number of protons in the atom's nucleus. Now, I know it feels like we've said this a million times already, but it's extremely important. Number of protons cannot change. You can only change the number of electrons. Okay, an ionic compound occurs when we take those metal cations and those nonmetal anions. Because cations want to get rid of their electrons, anions want to gain electrons, they make a really good pair. Okay, so let's relate ion charges to the periodic table. Okay, we talked about all the different groups on the periodic table, and each of these groups has a specific charge. So all group 1 metals, so that all that first group, are all going to form 1+ ions. So they're all going to lose 1 electron. Group 2 metals are all going to form 2+ ions. So they're all going to lose 2 electrons. Okay, remember, we're going to skip those transition metals in the center and go all the way over to group 3, and we'll look at a picture of this in a second. Group 3 metals all form 3+ ions because they all lose 3 electrons. Okay, transition metals form cations with various positive charges, so when we get into those, we'll talk about how to figure out what type of cation they form. Okay, now let's skip over to the nonmetals. Group 7 nonmetals, which are the halogens, all form 1- ions because they all gain 1 electron. And group 6 nonmetals, which don't have a specific name, all form 2- ions because they gain 2 electrons. Okay, and if we went to group 5, we're just going in order, so group 5 is going to gain 3 electrons or form a 3- ion. Okay, the group 8 nonmetals, which are the noble gases on the very end, remember we said that they're noble because they don't react. So if they don't react, they don't need to lose or gain electrons. They're already stable on their own, so they don't have a charge. We could think of them as a charge of 0. Okay, so here we have group 1. These were the alkali metals. Here are alkaline earth metals, and they're all group 2. Transition metals, we said, had variable charges, and then here we've got our last set of metals, which are +3. This includes things like aluminum and those metals. Okay, now let's jump over. We have noble gases, and we know that they have no charge because they're already stable on their own. Then we've got the halogens, which all gain 1 electron. Then the next group gains 2 electrons. The next group gains 3 electrons. Now here's the tricky part. This group can either gain 4 or lose 4, and we'll talk about later on why that is. But for now, just keep in mind that it's plus or minus 4. You will need to know these charges, and since they somewhat go in order, it shouldn't be too bad, but you're going to need to know them. You won't be given a chart like this that tells you the charges. Okay, so now we talked about ionic compounds a little bit, so let's go into that a little bit more. Okay, well, compounds that contain ions are known as ionic compounds. So, for example, table salt, which is sodium chloride, contains the Na1+ ion and the Cl1- ion. Compounds need to be neutral, and so that's why we have a +1 and a -1. And in ionic compounds, the positive and negative charges are really attracting to each other. Think about like the north and south pole of a magnet. And so ionic compounds usually have very high melting points. Salt's melting point is 800 degrees Celsius. That's really high. And it's because of that really strong attraction between the cation and anion. So it also has a really high boiling point as well. Ionic compounds on their own will not conduct an electric current. And water by itself will not conduct an electric current either. But if you put them together, they will conduct electricity because the water breaks apart the cation from the anion, allowing the electrons to be free to move around. And in order to conduct electricity, electrons have to be free to move. So an ionic compound by itself won't conduct electricity, but if you dissolve it in water and allow those electrons to move around, then it will conduct electricity. The other way to get an ionic compound to conduct electricity is to melt it, because then you're freeing up those electrons, and they can also conduct electricity in that case. Okay, so here's an example. Here's just regular water, so here's all of our water molecules, and we've got a little conductivity apparatus, and it's not conducting electricity. Okay, here we've got a whole bunch of salt, so you can see the sodium cation and the chlorine anion, but they're all bonded together in this very crystalline structure. And so the electrons aren't free to move around, and so it's not going to conduct electricity. But once we put water with the salt, the water has 2 parts, a positive hydrogen, a negative oxygen. So the hydrogens attract to the negative chlorine, and the sodium, see how they're all attracting to these negative oxygens? And so it pulls that apart and allows the electrons to move, which then conducts electricity. Okay, ionic compounds also have other characteristics besides their melting point. So an ionic compound is a metal with a nonmetal. Because remember, we said that metals form cations and nonmetals form anions. So we need that positive and negative component to go together. So usually for an ionic compound, it's going to be opposite ends of the periodic table, because metals are over here and nonmetals are over here. Like we said before, they have very high melting and boiling points because of that strong attraction between the positive and the negative, and it's very hard to break them apart, unless you give it lots of energy, so high melting point. Ionic compounds also conduct electricity when either melted or dissolved in water. They won't conduct electricity by themselves. That's because those electrons have to be free to move. Okay, we also know that a chemical compound must have a net charge of 0. Now the parts could be charged, but overall the total charge has to be 0 or neutral. So what that means is that we have to have positive charged things or cations, and we have to have negative charged things or anions. Both of those have to be present because we have to get it to be 0 at the end. And so the number of cations and anions must be such that the net charge is 0. We could have different amounts of them because their charges are going to be different. But overall, it has to add up to 0. Okay, let's look at a few examples. Okay, so we know that the chemical formula for table salt is NaCl. 1 sodium, which is a +1, and 1 chlorine, which is a -1. So when you put those together, we get 0. So that works out. We're always going to list the cation first. So the positively charged component goes first. In this case, it's sodium, and then the anion, which is chlorine. Okay, so what if we had magnesium and chlorine? Well, magnesium is a 2+, and I'm going to write these next to each other, just like we did before with the chemical compounds. It's like one word. Okay, and chlorine is a minus or a 1-. Now, if I had one each of these, it would be 1 times 2 plus 1 times -1, which makes this a -1. So it would be 2 minus 1, which gives me 1. Well, I need 0. So I need the total positive charge to equal the total negative charge. Well, if I have 2 positives, that means I need 2 negatives, and so that means I need 2 chlorines since they're each a -1. And so I'm going to use subscripts to indicate quantity. So now if I have 2 chlorines, that makes this a 2. So now I have 1 times 2, which is 2, plus 2 times -1, which is a -2, and now that gives me 0, and that's what I wanted. So what we're going to do is change the subscript to get a neutral compound. You can't change the charge, but we can change the quantity, because we're trying to write the compound. Alright, let's look at barium and oxygen. So barium is a 2+, oxygen is a 2-. Well, if I have one each of these, that's 1 times 2 plus 1 times a -2. Well, this is 2, and this is -2, and 2 minus 2 is 0. I don't have to do anything with that. I need 1 each. And so it's already good the way that it's written. Alright, what about lithium and nitrogen? Lithium is a 1+, nitrogen is a 3-. Okay, and again, notice I'm writing them close together. It's like one word, and I'm just making the charge a superscript. Okay, well, as it's written right now, I have 1 that is equal to a +1, plus 1 that is a charge of a -3. So I have 1 minus 3, which gives me a -2. I need it to be 0. So I need the positive charge to equal the negative charge. So I have -3, I need +3. And since each lithium is a +1, I need 3 lithiums in order to get a +3. So now I have 1 times 3 plus 1 times -3, and now I have 0. Alright, let's try one more. So calcium is a +2 and phosphorus is a -3. So I have Ca2+, P3-. So as it is right now, I have 1 times 2 plus 1 times -3. So 2 minus 3 gives me -1. Well, all these other examples, except for the barium and the oxygen because they were the same, I had one of my charges was a 1. I don't have that here. So I'm going to need to manipulate both of these. So I need to find a common number between 2 and 3. The only common number I can think of is 6. And so what that means is that I want my total positive charge to equal +6, and I want my total negative charge to equal -6, because then that will give me 0. Well, if calcium is a +2, that means I need 3 calciums to give me that +6. Just 2 times 3 is 6. And if phosphorus is a -3, I need 2 phosphorus to give me the -6. And so my overall compound ends up being Ca3P2. And you can write the charges, and that's totally correct. Some people don't like to write the charges up top, but I think it helps me to make sure I'm writing a neutral compound, so you can absolutely do that.